Anyone?
Are there standard tables
Standard tables.
that you can look it up?
Good answer. I don't know. Probably they will. But if now, Cole, if now we don't have the standard table, what will you do? Anyone? You guys are thinking very complex. Can you think simple? Help me over here, please. Think very, what can you do? Okay, we can carry out experiment. Okay, we're going to measure the nail pull out force. Okay, so we are going to measure the forces. Okay, you can use a spring gauge. Okay, something simple. I'm just giving a very lame or easy way, right? So you try to see how much force, or you try to measure how much force does it take to pull out this nail experimentally. Okay, that is how it is measured. Okay, now question for you. Okay, question for you. Why is it the shear? Why are we measuring? Why can we use the pull out in shear? Anyone? Right? So I just told you this, right? We're going to measure. So when you pull out the force, why is it in shear? Anyone, please?
Is it the shear force between the nail and the wood when you
slide? So is the sliding, yes or no? Right? Whether the nail come out or not, it all depends on the what? On the sliding. Okay, so I'm going to amplify. Okay, I'm going to amplify this. Okay, I'm going to amplify. So I'm going to blow this up. I'm going to blow this up. Okay, I'm going to blow this up. Right. So at the end of the day, right? It all depends on mu Rn. So Rn is the normal force coming down. And let's say we have an element, this is very bad, too excited. Okay, so let's say we have an element over here. This is our Rn, and this is our what? Our mu Rn resistance force. So over here is where we have our force P, right? P over here. Okay, our resistance force, how much we pull out. So this is our, you all can see where I'm drawing, yes or no? Right? So now the next question is, then why are we so focused on shear? Can you all see why we are so focused on shear, yes or no? Yes, no, maybe, anyone? Can anyone tell me why with this model or with this context, we're so interested in shear? Anyone? Are you there? Hello? Okay.
Is that because it'll fail due to shear?
Yeah, this is because look at mu Rn. Mu Rn, right? This is what? Parallel to the nail surface. Right? No doubt when we do this experiment, right? If you look at the P and you look at this surface over here, right? You look at the P and you look at this surface over here, it's 90 degrees. You tell me, Eugene, aren't we measuring normal stress? No, I mean the normal force. No. Okay. Now I have another. I have another analysis for you to think about. Okay. Now, Question for you guys. Does the length of the does the length of the nail affect the pull-up force? Anyone? Things drop.
Yes.
I repeat again. Hello? Someone trying to say something.
Oh, I just guessed yes.
I made the same guess. Okay, Jacob, I thought, okay, right. Longer nails, better joint. Question. Is friction a function of contact area? The answer is no. Okay, wait. Watch this. Okay, watch this. Up to a certain critical length. I repeat again. Okay, so let's say we have, these are two different pieces of wood. Okay. This is nail number 1. This is the depth. Okay, this is nail number 1. This is nail number 2. This is nail number 3. Okay. So for example, we have done experiment, okay, that at a certain distance from here to here, okay, at a certain distance, this is bar experiment. This is the minimum length or the critical length. Okay, sorry, I'll call this the critical length. Okay, so now nail number 1, nail number 2, nail number 3. Right? Okay. There will be a difference in performance between nail number 1 and nail number 2. And the reason why this is less resistant or lower resistance force due to shorter or due to length, okay, length less than critical. So this is what I mean by the critical length. Okay, for the other two, okay, for the other two, does not length will not make any difference. Okay, once you reach this critical length, it does not matter how long your screw is anymore. It does not matter. So I used to think, okay, I used to think the longer it is, the better resistance. No, not necessarily true. Okay, so a way to have it more resistance, okay, is how the nails are designed based on how you can apply a normal load or how mu can be increased. So if you see some of these nails, have you all bought nails to fasten wood before? Anyone? Right? You can see some of them are trying to put a bit of twist. Am I right? And some of them, the surface, they try to make it as rough as they can. Okay, this by making it as rough as they can is to improve what? To increase what? Mu, yes or no? Or having a twist. Okay, that's how they are doing it nowadays. Okay, the length, as long as you reach a critical length, it does not matter. Okay, so Cole, you're right. The length does play a part, but once beyond the critical length, it does not matter at all. Okay, right. So that is I hope you all learn from me. Okay, I make mistake from me. Okay, longer length, better resistance. No. Don't waste money. The longer the length, the more money you have to use. You have to pay. Right. So this analysis, right? You still apply rule number 1, where V and I are constant. See, still the same, right? Rule number 2, still the same rules. Remember this rule we derived, so datum of analysis. Okay, datum of analysis is at the centroid. Nothing new, right? Then rule number 3. Okay, rule number 3 is analysis will start at Y max. Okay, and rule number 4. Okay, rule number 4 is first moment of area. Don't write first moment too long. Okay, where Q cannot cross over the centroid. Nothing new, right? You know these 4 rules. The only thing that is new is the Q is equal to force that the fastener could resist divided by the spacing of the joint, right? Like as I mentioned before, these 4 rules you can apply from the beginning of the shearing stress chapter up to the end of the shearing stress chapter. Okay, enough of me yapping. Now we are going to look at an example. So I've posted the example on Avenue to Learn. Okay, so we are going to look at the first example. So example number 1. Where am I on this page? Do I have space here? I have space. So example number 1. Okay, so we are going to look at this example over here. You have this, okay? I've posted this on Avenue to Learn. Okay, I posted this. So this, then we're going to read it. And then we have this. Excuse me. Okay, we have this. Right. So we have a structure over here. So a double web girdle is constructed from 2 plywood sheets that secure to the wood members as its top and bottom. Okay. The allowable bending stress of the wood is 8 KSI, and the allowable shearing stress, which is sigma allowable, is equal to 3 KSI. If the fasteners are positioned at 6 inches and each fastener can support 600 pounds in a single shear configuration. Okay, determine the maximum load that can be applied to the beam. Okay, so let's see what we have. Okay, so when you see questions like this, you'll be like, why they are telling us so much information? Okay, so sometimes the information are useful, sometimes the information are absolutely useless. Okay, right. So let's do it over here, right? So this is our wood member. Right, and then this is our plywood sheet. Okay, so where the plywood sheet is, this is the plywood sheet. Okay, so if I were to draw our transformation, So this is our X and Y, rotation about Z. So for the cross-section view, this is Y, and this is our Z. Okay, then right-hand rule, this is rotation about the X. Okay, so so on the left-hand side, we have our cross-sectional